Okay, class, are you able to see my screen?
No.
No, doktor.
Okay. Okay. Now? So I believe you can see, right? Fundamental law integral form. Can you?
Can doktor.
Ya, doktor.
Thank you. All right, thank you. So, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to all of you. Today we're going to continue on fundamental law, which is the integral form. So before we begin, I would like to recap what we have learned on the last class. Alright, so basically this is chapter 6, where we learn about the static as well as a pitot tube. So we did the example 5, where we need to analyze the velocity at the static condition, alright, at the stagnation point. So from here, we do the manometry measurement. Alright, we can see it is a manometer, and then we calculate the pressure difference. The pressure difference, we need to substitute into the equation velocity square root of 2 multiply with the pressure change over density of air. Alright. Student may be confused, what is the density? This is the density referred to the flow. So as you can see, this is air. You should use the air density. And then some of you might confuse what's the difference when the PATM is, why the PATM equal to 0? Why the other is not equal to 0? Alright, just reminder, when the question is not stated anything special, just assume or consider it is under gauge pressure. When it is under gauge pressure, we consider PATM is our reference line. That means it is equal to 0. When it is specifically mentioned, the absolute, you can see the keyword absolute. When the keyword is absolute, you must use the absolute PATM, which is 101.325 kilopascal. Alright, so I believe you should know after this, if you go through my lecture note. Alright, for your test 1, I hope that you will study on the lecture given, as well as look at my video tutorial, how I solve the question. Alright, so I want to show you. Alright, if you go to my website, okay, if you go to my website, for example, people.utm.my/mnhidayat, you can see this web page. Alright, just you can see this is the menu. In this menu, you go to the tutorial and click chapter 2. In here, you can see a lot of tutorial question that I have solved in order to help you in your test and final. Okay, wait for a while. You can see as well tutorial chapter 4. Okay. Alright, in tutorial chapter 2, I have solved force on curved surface. Alright. I think I have 6 video. For this one, you can look at many video. Okay, this is 18 video. Okay, you can see force on plane area, buoyancy. Okay. If you want to learn, for example, this is tutorial 3, 4, 5, 6. Okay, the one that I send you the homework. Okay, you can look at and then study from here. All right. Same goes to the chapter 4, where today we're going to start on chapter 4, Renault transport theorem. This is all the question that I solved previously. You can look and understand. All right. So basically, that's all. Let's proceed on the today lecture. So in today's lecture, we're going to continue on the called fundamental law. So in the fundamental law, there are two options for studying fluid flow. The first, we can study the motion of individual particle. Secondly, we can study the region or space of the fluid flow. So now we're going to review the physical law as they apply to the system. Go over maths needed to convert from the system to a control volume. Obtain formula for the physical law by combining result. So the basic law, we start with the basic law of conservation of mass. So what is the conservation of mass? If you still remember, or okay, maybe this semester you are taking the thermodynamic, right? So the conservation of mass is the mass of a system is conserved and doesn't change with time. For example, mass of the system, okay, equal to constant. This is the formula where the change of the system, the change of the mass in the system is equal to 0. Alright, this is reflect to m dot equal to 0. So what it means, for example, you have the carbon plus oxygen, it will become CO2. Or hydrogen plus oxygen, it become hydrogen and oxygen, for example lah ya, it will become H2O. Alright, this is before and this is after. This is before and this is after. The mass of before equal to the mass of after, even there is the reaction and action. So I hope you understand, yeah, conservation of mass. When there is a change of when there is a reaction inside the system, before and after the mass change, it doesn't change the mass with time. Okay, the mass will not change with respect to time. Alright. Newton's second law, on the other hand, if okay, if there is a net force, which is F on the system, the mass in the system will accelerate. So the summation of force F equal to MA. In the other hand, we can have d over dt mv. You can see the change of velocity over time will get acceleration. So this is the Newton's second law, very simple. When there is a net force acting on the mass in the system will accelerate. And then we go to the angular momentum, which is the rate change of angular momentum is equal to the summation of all moment acting on system. So this is the symbol of angular momentum equal to dh over dt, where h basically represent the summation of momentum r minus b. Sorry, r minus b. And then multiply with the summation of moment. And then the first law of thermodynamic. The first law of thermodynamic, if heat Q, okay, is added to the system, or work is done by the system, dE must change accordingly. So this is the change of Q minus the change of W. Minus W means the work is done by the system equal to dE. This is system energy. Or we can simplify Q dot over, this is the work rate, yeah, dE over dt.
Doctor,
Yes,
what is the symbol X?
the small change.
The motion, the triangle.
Not the triangle, yeah. It is something like
Is it delta, doctor?
delta. Yes, it is the change. Okay, this is the change. Okay, this is small change.
Okay, doctor.
Okay. So you can look at the symbol. Basically, let me check. Small change. The symbol. It is like a S. Okay. For example, the small change here can be 0.001, something like that. This is the big change, maybe 3, 4. Right. The control volume. Okay, now I'm going to introduce you to the control volume. So why we use the control volume, and what is the control volume basically? Okay, so equation above are written for the system. All right. When we look at here, look at the beam. Okay, look at how beam deflect under load and can study piston as it oscillates. Alright, so the reason why we use the control volume because we need to convert from the system to the control volume. So this is basically the system looks like. I draw again. Okay, this is the beam. Maybe the T beam. Okay, the beam. Alright, and then we have the load. And then we have the support. So from here, this is basically the system. The system consists of all of this. Alright, it consists of the beam, it consists of the reaction force, okay? It consists of the reaction force, which is Ry, Rx, it consists of the weight of the beam. Okay, all this is called a system. So this system, in order for us to analyze the system, we need to convert into control volume. Why? Because maybe we need to analyze sequence by sequence. Maybe I want to analyze this portion, this region. So I convert here as a control volume. Control volume 1. Maybe I want to analyze this region. This maybe control volume 2. Alright. So for example, for the piston also, we can do the control volume in order to analyze how it oscillates. So from here, okay, we need to, right? So we need the basic law. We need basic law to be written to apply, okay, to a specific region in the area of in the area, okay, our interest. For example, I am interested to know the load in here, so I can segregate based on the area and assign as the control volume 1. So within the control volume, I only analyze the area. That means the control volume will never change. Okay, we will never change the area. The area, the region will be fixed there. So now we need to use the Renault transport theorem, which is used to convert from system to control volume. We use RTT. Okay, as you can see all this equation, this is all in terms of system. As you can see all in terms of system. Okay, this is all in terms of system. Now, in order for us to analyze in detail, because we need to study the motion of individual particle, and then we need to study the region of space, the fluid flow, we need to divide the space, we need to divide the system into separate or a few of the control volume so that we can analyze further. So based on all the law the fundamental law that we have learned previously, like angular momentum, Newton's second law, first law of the thermodynamic, all these based on the system, not the control volume. The reason why we need control volume because we need to analyze, okay, the fluid particle flow in that region. So how to do that? This is the method we call a Renault transport theorem. We call as RTT. So the fluid system, specific mass of the fluid within the boundary defined by the closed surface, shape of the system may change over time. Alright. This is the definition of system. For example, a fluid system. The specific mass of fluid within the boundary defined by the closed surface. Okay, the shape of the system may change over time. For example, fluid flowing through a constriction. So that means the gas is compressed. Alright. Yeah. Alright, for example, we have the nozzle. And then we have the fluid. This is fluid particle. Over the time, the fluid will move from left to the right. So all of this we consider as the system. Okay, for example, this is the system. The fluid system. It will change. Okay. That means the region will change because this is considered fluid system. As fluid move and deform, the system move and deform. Alright, you can see here, this is a system. The system will follow the fluid. As the fluid pass, it will go through to the next region and until the last section. Control volume, on the other hand, is a fixed region in space which doesn't move or change shape. Usually selected as a region that fluid flow in and into and out of the system. Alright. Okay, this is often choose boundary to coincide with some solid or natural flow. Boundaries. For example, we have the nozzle, and then we know that at initial point, the fluid will flow here. This is the fluid. Okay, this is the fluid. And then the fluid system consists of this surrounding the fluid. Alright, when we define the control volume, normally we assign the same location as the system, which is here. Okay, however, as the time goes by, the fluid will move, but the control volume will fix there. Okay, it will be like this. Okay, this is control volume still there. But the system will change. Okay, this is for the system. Okay, now you can see the difference. The red color, this is a fluid system. And this purple color represent a control volume. It is a fixed region. at time, alright, at time t, the control volume and the fluid system coincide. Alright, this is at the initial point. Let's say we have the diffuser. Okay, this is diffuser. At time t, this is the, okay, the red color represent the system, the fluid system. This is the fluid. Okay, this is fluid, yeah. Okay, make it like this. Alright. Okay, this is at the time t. This is the system. Or the fluid system. And then when we want to investigate, we define at the initial as the coincide. Okay. The same location as the system. Okay. That means it is coincide. So here is a control volume. Okay, let's say this is 0.1 and this is 0.2. The fluid will move from here, the system of fluid will move from here to here. Alright. And then, okay, during delta t, the system moves in the flow direction at uniform speed from V1 to V2 or at section 1 to section 2. So how it looks like? It will be like this. Okay. The same thing, this is diffuser. Okay. At initial point, it is coincide with the, you can see coincide with the control system. And the control volume coincide with control with the fluid system. So maybe like this. Okay. Not the same lah. Try to make it same. Alright. Alright. This is at time t. Initial. Alright. After the time pass at delta t, during delta t, okay, the change of time, maybe from 2 to 3. Okay. So they change in 1 second. So this will move, okay. The fluid system will move from here to the next position. Okay. Remember the control volume fixed. The system will move. Okay, this is the original control volume, which is mass fixed. And we have the flow from here to here, from left to right. And then we need to define the region. This is I. Okay. And then this is double I. This is 1, this is 2. Example, like this. Okay, let's name this region section 1 and section 2. So, this I is a region uncovered during delta T. Okay, delta T. Of course, it is uncovered. However, for the region 2, new region, covered by fluid system. So, however, this is not part of control volume. At T plus delta T, the system has the same fluid, but it occupies the region, okay, control volume. Control volume, that means the original control volume here, it is fixed, minus I, okay, minus this region, and then plus with second region. So this is the system. Yes, it is true. The green color here represent the system. As in order to get the green color, which is the system, CV, which is CV here, okay, the CV here must minus this one plus with second region. You will get the green color. Okay, do you agree, class? Do you agree on this concept? Do you understand now? Yes, yeah? Yes or no? Okay. Back. Okay, plus with this. Okay. This is as the time goes. Okay, T plus delta T. The system has the same fluid but occupy the next region. So from here, I want you to understand this here. This is very important. CV minus I plus 2. Remember the control volume is fixed in space. So B of the system equal to B of the control volume at time T. That means at time T, the system has coincide with the control volume. Okay, do you have any questions so far? Okay, class, do you have any question?
No, doctor.
Are you sure?
Doctor, did that mean that CV also can equal to the second region minus 1 or 1 minus second region?
CV?
Yeah, the
Okay.
control.
Yeah, it can also. But now we want to focus the system. How to get the system? CV minus I plus 2. Okay, this is for system lah ya. For system. Alright. If you don't have any question, I have a question for you. Why you not ask what is B? I purposely introduced the B and no one asked what is B. So what is B? I ask you. Do you have any clue what is B? What is B? It is not the boundary, yeah? What is B? The B, the B basically is the extensive property. So what is extensive property? Normally, when we deal the property, the physical property of the object or the system, okay, for example, we want to investigate the temperature, we want to know the property like temperature, velocity, the volume fraction, the mass flow rate, all of those we consider as a property. Now, in order for us to classify what kind of this property, we can categorize into two, extensive property and intensive property. So extensive property is the property that relies heavily on the mass, okay, volume and entropy. Okay, that means when you give the additional of external force or external of the mass, it will change based on the quantity. So for example, volume 1 plus volume 2 equal to volume 3, right? So it changed with the quantity. So what are the things that not change with quantity? Any idea? The property not change with quantity.
Density.
Okay, density. The temperature?
And pressure.
Okay, yes. The temperature also not change with the quantity. The color, for example, color red color plus blue color, is it change with quantity? It will not change. All right. So that means now we look at the extensive property, which is rely heavily on the mass. Okay, when we put something on A, it will change to B. Okay, that is the extensive property. So this is at time t. Okay, B system, extensive property of the system at time t equal at control volume, which is coincide, yeah. And then this is after t plus t1, t plus delta t. B of the system, okay, at time t plus delta t equal to B CV of the system, this is control volume, T plus delta T, okay, minus B, region I, T plus delta T, plus B, region 2, T plus delta T. Where do I get this? From here. Okay, you can see this is CV, this is negative region I, and this is plus region 2. Okay, this is system, this is for system. I hope you understand, yeah? This is the extensive property after T plus delta T. Okay,
Doctor,
yes,
the BI also at the 3 plus delta t or at t?
at T plus delta T.
Oh, okay. Will not the BI equal to B2? I mean the B1 equal to B2 at 3 plus delta t?
Which one? Which one?
The extensive property.
Mm-mm.
It's not the for the system in extensive property in system 1 equal to the extensive property is system 2 because it's just the chain of time, right?
Mm-mm. Okay, basically I want to show you, this is in terms of at time t. Okay, this is at t plus delta t. So what happened? Okay, at time t, the system coincide with the control volume, right? After t plus delta t, refer to this one. In order to get the system, okay, control volume minus region I plus region 2. So, the extensive property of the system at this time equal to control volume, okay, at this time minus region 1 plus region 2. Just want to show you the difference in terms of time.
Oh, I see, doctor. Thank you.
Okay. Alright. After that, okay, subtracting the first equation from the second one and divide with delta t. Okay, I want to subtract only. So equation what? The first equation from second one. Okay, so that means this one minus this one. Okay, so from here, okay, you can put B of the system minus only. Oh, sorry. B of the system at t plus delta t. Okay. Minus B of the system at t. And then equal, you just minus only lah. Alright, this is continue. Continue here. So, B of the system okay, B of the system T plus delta T minus B of the system at time T equal to B control volume T plus delta T minus B control volume at time T minus BI I plus, sorry, this is T plus delta T plus B T plus delta T. This is all of these must divide with time. Okay. Alright. So taking the limit, okay, delta t approaching 0 and using definition of the derivative, we will get this one, okay, the derivative of B of the system minus dt. Okay, we simplify lah. Okay, because this is the change. Okay, minus, right? So the different equal to different. Equal to d B of control volume minus dt. And this one, okay, just minus B. This is over time, we have put dot as the rate. Input plus B output. Okay, why suddenly we have to consider input and output? Okay, you can see region I is considered as input. Okay, this is input. Region 2 considered as output. So we name it as an input and output, in and out. So this is the Renault transport theorem. Okay, Renault transport theorem. Okay, so letting. Okay. Let B equal to B over M. Alright. Okay, before that, I want to show you B is a extensive property, right? Extensive property relies on mass. So that means the B is relies on mass. Relies on mass, right? B relies on mass because it is extensive property. In order to make it equal, we have to put constant, which is B. B equal to Bm. So, in order to get this B, capital B divide Bm. Then you will get small b equal to B over M. And B control volume is equal to integration of rho B dV. Okay. Let me show you how it works. Okay. This one, which one ya? Rho dV basically is equal to dm because density equal to mass over volume, right? So mass equal to rho V. So dm equal to rho, the change of volume. Okay, simple way. And then we do another term, integration of B. Okay, since this is B dm, this one and this one refer to dm, right? So B dm is basically how much the B is in the control volume. Okay. It's basically how much. Okay, B is in control volume. Integrations of B over M dm. The same thing. Right, this is just explanation. So I want to replace the equation here. Okay, from here to here. D B of the system over dt equal to, okay, alright, this is d over dt. Replace this one, dcv, with this one. Okay, I replace here with the integrations of control volume rho b dv minus with b1 rho v 1a. This is velocity, yeah. Okay, represent this one. Minus, and then this is plus, represent this one. Later on, I will explain. 2 rho 2 v2a. Okay. Now, you must be confused why we have this kind of form. This form and this form. Why I expand? Okay, I want to show you the reason why. Okay, because B, okay, this is the initial one, yeah, BI, this one. Okay, this one. B input, or this one, yeah, which one? Okay, B input. Okay, BI T plus delta T is equal to B multiplied with M. Okay, B1, M is M1 time plus delta T. It's not plus. Plus delta T. Alright. So from here, B1, mass. How to get the mass? Mass is the rho multiplied with volume, right? Okay, this is one, this is one. This is T plus delta T. Okay. From here, the volume is, I want to expand further. B, okay, from here, the volume here is basically equal to the velocity multiply with delta T multiply with the area. Okay, do you think the unit is the same? Okay, let's look. The unit of velocity is meter per second. Multiply with time, second. Multiply with the area, meter squared. So what would you get? Class? Velocity multiply with time, multiply with area, what do you get? Meter
Cube.
Meter cube is the volume, right? So, I want to replace B1, rho 1, volume with this one. Velocity, delta T, area. Okay. So, okay, and okay. B input, this is dot. Remember we have dot. What the dot mean? Anyone knows what is dot mean? It is over time, right? It is the rate. Okay, when you have the dot at the top of the parameter, it is the rate over time. So, it is taking the limit at delta T approaching 0. Okay, B I T plus delta T over with delta T. Okay, so limit delta T approaching 0. B we replace with this one. Okay, B1, rho 1, V1, delta T, area 1 over with delta T. So can we cancel delta T? Yes, we can cancel delta T, delta T. What do we get? It is basically we have, okay, we have B1, rho 1, V1, A1. So is it the same like this? Yes, it is the same like this and this one. Okay, you can see the change from B here. I convert into this form. Okay, this is the whole of explanation. Explain conversion. Okay, I hope you understand how to convert this. Right. This is input. Same goes for B output, which is B2 rho 2 V2 A2. Right. Above description, for example, we have one inlet and one outlet. Okay. For example, we have the nozzle. We have inlet and one outlet. We can generalize the theorem for multiple inlet and outlet. Okay. This is only one inlet and one outlet. When you apply, for this case lah, you have the flow from here to here. You can apply, this is region 1, this is 2. Okay, you can apply directly this equation. You can see the extensive property of the system, B system, equal to the change of property inside the control volume minus the flow into and plus out of the control volume. So consider we have the multiple inlet and outlet. Okay, we have something like this. Alright, we have the flow. Okay, we have out of the control volume, which is normal vector. Then we have the maybe the second one, and maybe this one. Alright, and then we have the mass entering. Okay, mass enter. This is control volume. Okay, and then the area here, okay, we consider here is the change of area, dA. When you look at from this view, you can see the area from that side. The N here is unit vector that point out from control volume. The flow rate of property B through dA is given by rho B V dot N product multiply with dA is equal to B rate out minus B in. Okay, so that means this term must be normal to dA. Okay, you can see it is normal, shall be normal. Okay, thus we can apply from this equation, the one that we derived, right? The change of the extensive property for the system over dt is equal to the change of control volume rho B dV, okay, plus the change in control surface, okay, dot N dA. So that means the change of control surface, we are looking at anything, property or quantity that cross in and out of the control volume. So this is referred to the control surface. And this is referred to inside the control volume. So when we try to convert from the system to the control volume, we must understand in control volume, we have two components that need to be considered. Inside the control volume, the change inside the control volume because we have over time. And then what the property that cross in and out of the control volume, which is control surface. Okay, now since we understand the general form of Renault transport theorem, how to convert from the system to the control volume, let's apply to the conservation of mass. Remember previously our fundamental law mentioned that the conservation of mass, where is it? The conservation of mass. This is dm over dt equal to 0. That means the mass of a system is conserved. This is for the system. Okay, I mentioned again, this is for system. How to change from dm to dt, dm over dt to the control volume? Okay, I want to change in the form of control volume. So by using the conservation of mass again, okay, recall dB of the system over dt is equal to dB of control volume over dt minus width b rho. Okay, this is velocity area plus okay b2 rho v squared 2 area. Okay, this is recall back the one that we have derived previously, this one. Okay, this one lah ya. So this is refer to the change in control volume. This one refer to the control surface. So let B now, okay, our extensive property. Remember, it is any kind of property like mass, volume. Let's say let B equal to mass because this is conservation of mass, right? Now we consider the B as a mass. Okay, the property now is the mass. So that means the flow now is considered as the mass. The flow in and out of the control volume is the mass.
Doctor,
Yes.
can I ask what is CS?
Which one?
CS.
CS.
Yeah.
CS is a control surface.
Oh, okay.
Yeah, control surface. That's the matter or the property crossing the control volume. Okay, this is control volume, right? Okay, surrounding the control volume is the control surface. It is a surface, that means it is the area. Okay, all this is the control surface. So now let B equal to M because we are dealing with the conservation of mass. So I want to replace anything pertaining to the B in terms of mass. Alright, so d M of the system over dt equal to d M control volume over dt minus B. Okay, this is B and this is M. In order to get B, which is B capital divide with mass. Okay. So, B capital is mass. Divide with mass. I will get the small b, right? Okay. And row 1, V1, A1. Plus mass. This is 1, this is 1. This is mass 2 over mass 2. Row 2, V2, A2. This can cancel out. Okay, cancel out. We will get, alright. Okay, we will get this term for conservation of mass. For conservation of mass, where mass of the system is conserved, that means no change. So mass flow rate equal to 0. The one that I have explained before, this one, yeah. Okay, where is it? This one. M equal to mass flow rate equal to 0. This is considered mass is conserved. Alright, so this is for system. So where is the mass for the system? This one. We can cancel out equal to 0. So what we left now is 0 equal to, okay, this is mass. I want to convert into mass equal to density, volume multiply with density. Okay, this is the conversion, yeah. So 0 equal to dm, which is the volume, d control volume over dt. The only change is the density, yeah. The volume is fixed. Okay, when we are dealing with the control volume. Minus which, okay, row 1 V1 A1 plus row 2 V2 A2. Okay, now I rearrange the equation. Row 1 V1 A1 minus row 2, okay, row 2 V2 A2. Okay, I can put this way lah. It is better. A first, okay, because alphabets. A1, A2, sorry. A2, V2 equal to this one. V, D, rho CV over DT. Okay. And this is we call as a continuity equation. This is the inflow and this is outflow. So we can write in integral form. Okay, 0 equal to the change of time control volume dV plus control surface rho V dot N dA. Alright. This is the conservation of mass leading to the continuity equation. Alright. Above equation is one-dimensional, right? The above one is one-dimensional, which is we have one inlet and one outlet. Okay. So a fluid in which all condition at any point is constant with respect to time. Okay. So for example, this case, when it is constant, the fluid is constant, there is no change of property over time. That means the density will not change over time. So we can have what? We can cancel what? Okay. For example, under steady state condition, steady state condition, no change of property, that means the density over time. Okay, the change of density over change of time equal to 0. So we can cancel out the whole of this term. So what we left is basically this term. Only control surface. Alright, so this control surface, when it is equal to 0, we can write down in the form of rho 1 A1 V1 equal to rho 2 A2 V2 is equal to m dot. Okay, this is mass flow rate. Okay. rho AV. After you expand, you will come in this equation. Okay, when this is considered only one inlet and one outlet. You have 1 and 2. Okay, you have flow from 1 and 2. Okay, that means you need to use this equation lah. Rho 1 A1 B1 equal to rho 2 V2 rho 2 A2 B2. Okay, so that means the rho at 1, area at 1, velocity at 1, rho at 2, area at 2, velocity at 2. Okay, if the area 1 and area 2 is the same, we can cancel out A1 equal to A2. Okay, if the density is same, density 1 equal to density 2, that means velocity 1 also velocity equal to velocity 2. So the above equation is one dimensional only. If not 1D, M flow rate, okay, this is typo. The M flow rate, M dot found by taking integral of this one. M control surface is basically integral of control surface rho B dot N and product multiply with A. Okay, this is for multiple inlet and outlet. Like this one. Can you see the flow from here? We have inlet 1, inlet 2, we have outlet 3, outlet 4, outlet 5. So you have to integrate, okay, in order to get the output. Okay, inlet 1 and outlet. Okay, this is inlet. This is outlet. You can see multiple of flow. Inlet we have 2 flow, outlet have 3 flow. So if the change of density over time is very, very small, we can call this as nearly incompressible fluid. That means it is hard to compress. The change of density is so small. We can consider it is under incompressible fluid. So we can neglect the control volume here. Okay, the change of density over time, dV term, and get the density V dot N dA as, okay, density is outside because the density is constant. Control surface V multiply with area equal to 0. Thus, the control surface is a V dot N dA equal to 0. Okay. Where the density? The density we go to the right side because this is 0. We move to this one, it will become this one. Okay. So now when we consider we have a multiple input and multiple output, we have inflow and outflow. So we can do the flow like this. Okay, the summation of input, inflow, okay, velocity at 1 multiply with the velocity must be perpendicular to the area, yeah. Multiply with I. This is okay, this is out. Equal to this is in. Okay. So V multiply with A. V is velocity, right? Velocity is, as mentioned before, velocity meter per second. Multiply with Okay, area which is meter squared. So what you get? You will get meter cubic per second. So what does it mean? Meter cubic per second. What is that? What is meter cubic per second? Any idea? What is the meter cubic per second? Volume. So this basically is a volume, flow, rate. Rate is per time. Okay, volume, flow, rate. So here, the summation of Q out equal to summation of Q in volume flow passing through the cross-sectional area. Okay. We do one example. Okay, and then we're gonna have activity. Okay, example 1. The inlet velocity of vacuum cleaner is a rectangular. Okay, inlet section of a vacuum cleaner is a rectangular 1 by 5 inch. The blower can provide suction at 25 feet cube per minute. Alright, let's draw the vacuum. Okay, rectangular. Okay, maybe this is 1 by 5. 1 inch, 5 inch. Okay, we have the suction. This is difficult like this. We have the vacuum lah like this. Okay. We have the inlet and we have the outlet. This is the suction. This is 1 and this is 2. And the area here is 1 inch by 5 inch. So what is the average velocity at the inlet? Alright. Okay. Now the question asks what is the average velocity V inlet V1. Okay, so we can apply Q in equal to V in multiply with the area in. Okay, based on our previous equation. Q equal to A multiply with V. This one, yeah. Okay, consider this is negligible. Okay, assumption. The air. Okay. Assumption, yeah. Assumption air under incompressible flow. Okay, that means there is no change of density over time. So when it is no change of density over time, we can use this formula Q out equal to Q in. So how to get Q? Q equal to A multiply with velocity. So from here I can get velocity. So velocity equal to Q in over area in. Area I can get 5 multiply with 1. So Q. The question asks in the unit of meter per second. So what should I do? I need to convert Q first. Okay. My Q is right. The blower can provide the suction. Okay. This Q is equal to, this Q2, okay, Q1 equal to Q2. Alright. There is no change. Because of this one, you can see Q in equal to Q out. So I can say Q in Q1 equal to Q2. So at the suction is Q2, right? So it is given Q suction. So Q suction is 25 feet cube per minute. Alright, now the question asks meter per second. I need to convert lah from feet to second. Sorry, from feet to meter. So 25 feet cube per minute multiply with, okay, 1 minute. I want to convert into SI unit equal to 60 second. Okay, so I will get here is 0.417 feet cube per second. Right? And then the area as well. The area is given 5 inch. Okay, which one? 5 inch multiply with 1 inch, which is 5 inch squared. I need to convert into feet because I want to solve first. So 1 feet cube, 1 feet squared equal to 144 inch squared. You will get 0.0347 feet squared. So I can get the Q now, Q in. So that I can get the V in. V1 ya, V1 equal to Q in over in 0.417 feet cubic per second over with 0.0347 feet squared. Cancel, cancel. 12.01 feet per second. Convert directly into meter per second. So 1 feet equal to 0.3048 meter. Okay, you will get 3.66 meter per second. Alright, the question B, if condition are sea level standard, what is the mass flow of air? Okay, the question asks mass flow rate. Okay, the unit is kilogram per second. This is M flow rate. So M flow rate is rho AV. Just multiply with the, okay, the density. Okay, so another one, AV is referred to the volume flow rate. So rho multiply with Q. Thus, this is question 1, the question A, the question B. In order to get mass flow rate, which is rho AV, this is considered as a Q. Okay. So, the question again. Okay, nothing. Okay, it is given that the density of, okay, under the normal condition, okay, the density of air, okay, you can look at the table, density of air, okay, equal to 1.255 kilogram per meter cubic. Okay, you can refer to the table later on. In the exam, it will give you the table or it will give you the value of density of air. Don't worry. So, why you need the density of air? Because the formula require it. Density multiplied with Q. So, again, my Q here is, alright, my Q here is, okay, Q equal to A multiplied with velocity. So Q, my Q here is, where is Q? Okay, given the Q, this is Q, 25, okay, 25 feet cube per minute multiply with, I want to convert, yeah? I want to convert. do the conversion. Okay, I want to convert from feet cube per minute into meter cube per second. So I do the conversion. 1 feet cube equal to equal to 0.3048 meter. This is bracket, yeah, because this is the power of 3. This is 1 feet. Okay, make it like this if you want to convert. Multiply with 1 minute equal to 16 seconds. So you will get 0.0118 meter cube per second. Okay, why you need to convert into meter cube per second? Because you want to use this value density in SI unit. Alright. So mass flow rate equal to rho Q, which is 1.2255 kilogram per meter cubic, multiply with the Q in SI unit 0.0118 meter cubic per second. Cancel meter cubic, you will get 0.0145 kilogram per second. Okay, any question? Okay, class, any question before we proceed to the next activity? Alright. If you have any question, you can inform me later. Let's have activity, recap what you have learned. Okay. Okay, class, just to let you know, after this, we're gonna meet the, what we call, the semester break, right? The first semester break. Okay. And then another lecturer will take over for the next lesson. Okay, let me share it to you. Alright, class. Can you see? This is course information. We have covered week 1 until week 7. Fundamental law, integral form, where we use the RTT, Renault transport theorem, to convert from the system into control volume. So we derive the control volume for the conservation of mass. Remember, the summation of mass input in terms of flow rate equal to the mass flow rate output. Alright. And then we will have the semester break. And then this lecture will be taught by Encik Nur Musa. Okay, my partner will give you a lecture on conservation of mass, energy until this one. Alright. In the meantime, okay, within the semester break, I'll give you a project you can do within 1 week. The programming project that require you to solve using a MATLAB. I believe you have learned, alright, during programming using the MATLAB or Octave on how to solve the complex problem, right? This is the individual project I will give you to solve, all right? This programming assignment contribute contribute 10%. Okay, supposedly you have to work on it on 4 hours. Okay, I give you 4 hours only to solve, but I give you 1 week, all right? You need to, I give you plenty of time to solve it within 1 week, all right? I need to see your creativity on how to solve it. Okay, so assignment 1 that I have sent to you before, assignment 1, 2, 3 will be accumulate and contribute 10%. Programming assignment using the Octave or MATLAB, contribute 10%. This test 1, 23 November, please score well. Make sure your mark is more than 10, okay, 10%. 1 hour and 15 minutes only. And test 2, 20%. The final, 40%, alright? I hope you score in your exam, in your test 1, alright? So remember after this, Encik Nur Musa will guide you lah on week 9.
So doktor untuk assignment MATLAB tu doktor bagi before semester break lah.
Betul. Yes, correct. I will send to, I will upload in the e-learning lah, the programming assignment.
Alright, doktor. Thank you.
Okay, before we end our class, let's have the activity. Go to your e-learning. What have you learned on control volume? Right. Wait, yeah. Let me open the forum. What have I learned? What do I learn? Okay, give at least 4 points. What have you learned? Okay, for section 11, I have created a forum what I have learned on integral form, bracket RTT, and control volume. Please do so. I give you within 20 minutes. All right. For section 12, I have created as well. Give at least 4 points. And for section 13, okay, you may start now. As well as section 14. Okay, please, before the end of the session, I want to see all of you give your point of view. What have you learned on Renault transport theorem? Okay, what is the extensive property? What is intensive property? Giving example. Okay, I need to see your effort. Please, everyone, start now. I give you 20 minutes from now. Okay, please do so. Okay, class. Time's up. Let's check your feedback. Okay. This is for section 11. Alright, we have Yuvanisha. Thank you. What I have learned. A function of Renault transport theorem which is used to convert. Yes, correct. Review of physical law and apply. Okay, this is okay. Study of motion in vertical. Closed surface. Okay, that is good lah. Okay. And then let's check Fadil. Muhammad Haris. Okay, I learned about Renault City. Okay, what do you learn? Okay, you can write the equation. Okay. Extensive property. Okay. CV. Okay. Good. Okay, I have learned about the derived equation. Okay, that's Ina Salsabila. Okay. Color and temperature example of color and temperature are the example of temperature change. Okay, color and temperature are the example of intensive property. Okay. Which value does not change as the amount of substance. Okay, this should be intensive lah. The two different symbol of change and small change. Okay, derivation that result in the equation of mass flow rate, Renault transport theorem. Okay, Renault transport theorem is used to convert system to control volume. Control volume consider control surface and change in control volume. Alright, we have only 3. Okay. Okay, good. Okay, we go section 12. What I have learned. Okay, so many. Let's see Hidayah. I learned the 4 basic law. Okay, good. They use control volume, do the same, be deflect. Okay, learn Renault transport. Okay, after you have learned, please revisit back after the class, yeah. Okay, Li Chi Ying. Okay, good. I prefer like this, the equation. Okay, the one that I have taught you in the class. Okay. Anthony, basic law, control volume is fit region. Okay, yes, good. Okay, let's say lecture section 13. What I've learned. Wow, we have so many. Okay, let's see Samuel think math. Wow, this is good. So many that you have learned, Samuel. Mass always the same. Okay, conservation of mass. B extensive property, yes. B system, yes. Okay, good. Volume, flow rate, okay. Yes, incompressible, yes. Density, no change. Okay, mass flow rate, density, yes. Rho AV, Renault transport theorem, yes. Excellent. Okay, we look at Fakrul Amin. Okay. Okay, mass does not change with time. Okay, derivation of okay. Okay, Nadia Asila. Okay. Conservation of mass does not change. Okay. From the conservation of mass, you can put this way. The extensive property, in order to derive the conservation of mass, we consider the extensive property equal to M. And then we can segregate into control volume and control surface. Okay, finally, section 14. Only 2. Okay, Timothy. Okay, you learn this correct. Control volume to convert fluid system. Yes, doesn't change. Conservation is conserve. Okay, what is conserve? You can see lah. dm of the system over dt equal to 0. Okay. Okay, you have 4 as well. Alright. Okay, want to see your activity that you have learned so far. Okay, good. Okay, good. Okay. Okay, excellent. Alright. Okay. This is last activity. Okay, basically the reason why I advise you to give the feedback pertaining on what you have learned is where you can have the active learning. You learn and then you type the information from your brain. So from there, you can sustain the information more than you do nothing. All right. If you really want to score and remember well during the exam, please follow my advice. Please give your input as much as possible. Maybe you can give more than 10. Okay, the more you give, the more you get. Okay, the more you give, the more score you will get. I hope. Okay. I think that's all for today. Thank you very much for your participation, everyone. If you have any question, you feel free to let me know. All right. I think that's all. I think that's all lah. Okay, I end my session with Assalamualaikum warahmatullahi wabarakatuh. Good luck and all the best.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Thank you, Doctor. Waalaikumsalam.
Thank you, Doctor.